Nature's Archive Podcast, a Jumpstart Nature production.
Did you know that there are living trees in the United States that are approaching 5,000 years old? I'm not even talking about those that clone. I'm looking at you, Aspen. These are trees that are standalone, and you can find them right where I live in California. Imagine if those trees could talk. Well, in a way, they can. That's where dendrochronologists like Dr. Grant Harley come in. And it turns out that the science of dendrochronology is so much more far-reaching than I ever imagined. Dr. Harley today tells us how he reads the trees, inferring things like climate patterns, wildfire history, and community ecology. But this unique science even allows for dating artifacts such as coffins, cabins, shipwrecks, and other wooden objects. We cover all of this and more, including how tree rings are assessed without killing the tree, and how technology is used to make these assessments. Dr. Harley also answers why trees in the western U.S. make better specimens for assessing historical climate. And just what is the medieval climate anomaly? Well, we're going to talk about it, and we're going to talk about why it's important to us today. I feel like Dr. Harley could make a series of podcasts about dendrochronology and the history that it tells us and the mysteries it helps us solve. So I hope you enjoy today's introduction. Without further delay, Dr. Grant Harley. Dr. Harley, thank you so much for making so much time to speak today.
Of course. Glad to be here.
As we were chatting here in the run-up before actually hitting the record button, I'm super excited about this discussion because it seems that everything you do, everything that's on your webpage anyway, are all areas of keen interest for me, things that I've always been interested in, even before I took more of this ecology slant. So many topics I want to get into today. I hope we can do it all.
Yeah, let's do it.
All right. So why don't we just start real quick with who you are and how you got to where you're at. Can you tell me, where did you grow up and how did you get interested in, I'm going to say nature, and it's a very broad definition of nature.
No, that's perfect. So I'm a Florida man. I was born and raised in Central Florida in a town called Lakeland, which is between Tampa and Orlando. So it's a heck of a place to be from and kind of grow up.
I've driven through there a couple times.
Yeah. Good thing you're not hurt because, Interstate 4 is the interstate that goes between Tampa and Orlando. It's like the most dangerous interstate in the country. But so it's like growing up in a parking lot. But that's what I love about Florida is that it has a lot of natural areas still. And so I was able to, escape, explore through the woods, swim in freshwater springs. And that's kind of what draw me first to kind of nature is just being surrounded by it, being able to explore in it. And so, I was born and raised in Florida, went to high school, everything in Polk County, and then went to University of South Florida in Tampa for bachelor's and my master's in geography. And from there, I went up to do a PhD in geography at University of Tennessee in Knoxville. Spent 4 years there, graduated in 2012, and was lucky enough to get a professor job right out of finishing my PhD at University of Southern Mississippi. And so then bounced down to Hattiesburg, was there for 4 or 5 years, and this job came up. And I was thinking with kind of the tree research that I do and studying the environment, there's arguably no better place than Idaho with a lot of public lands and natural spaces. And so applied for the job, lucky to get it. And we moved here in 2017, been here ever since.
Nice. And I want to talk about geography for just a moment, because looking back on my own educational pathway, I think if I had realized how broad geography is, that probably would have been the route I went. What's your pitch to people who want to get into nature? Like, why geography?
Oh my goodness. Yeah. So this could be a whole nother episode of the podcast because I love flying the flag for geography because I'm a geographer by training and that's where all my degrees are in. It is a discipline that's kind of at a crossroads in this country, broadly in North America, where they're kind of searching for an identity because it's tough. Going back to your question and what I pitch to students is it is so broad, right? It's so broad. So it's a little nebulous I'm thinking early career students' minds like, well, what job can I get if I major in geography? And so it's really, that's what I use the intro class that I teach as a platform to kind of explain all the different jobs that are available, all the different kind of issues and questions you can address by getting that kind of broad training in geography that I had. And it's a fantastic discipline.
Yeah, there's so many branch points. I actually went back to, I try to occasionally take classes just to fill in the blanks in my own personal education. And I took a geography class at a local community college here a few years ago. And that was my eye opener because I was always great with maps, and I always thought geography was just maps. And then I knew weather was sometimes like, meteorology was in geography. But yeah, there's geology. You could get into political science from a geography perspective.
Yeah, we have actually a geographer on staff here he's a political geographer. So he studies geopolitics and conflict, immigration, all those issues, movement of people, especially right now in Ukraine. I think he's actually in Ukraine right now or on the border of Ukraine. But that's geography. And I'm similar story. I started at USF in Tampa. I think finance. I was a major in finance, and then I moved to something else. And then I took an introduction to geography class. I was like, oh my gosh, light bulb went off. Realized it's really broad. You can study the environment. You can study people. You can study marketing. It's such an eclectic and synthesizing discipline that draws on a lot of other disciplines that it just really appealed to me.
Yeah, it's probably a good place for people who aren't quite sure which direction to go.
Totally.
As you went down your path, some of the things we're going to talk about today, your studying of trees and tree rings and paleoclimatology and all these different things. How did you start to focus? I mean, it's still broad, but how did you begin to focus throughout your collegiate pathway?
So I started in caves, which is arguably the opposite of trees. So I was a caver growing up, loved exploring caves. It's the kind of the exploration aspect of it, and actually being certain that if you dig a hole in the ground open and it's a cave, you're 100% certain that no one else in the history of humanity has been in that space, which is pretty cool in my mind. Realized, of course, going through again undergraduate, you can actually study caves and paleoclimates by looking at stalagmites and cave growth forms that exist in those environments. And so that's the path I took during my master's degree. When we got to Tennessee, there's a really charismatic dendrochronologist that was there at the time. And I think he gave a talk the summer that I got there. I was like, I'm switching to tree rings, and I haven't looked back. So I've really only been studying tree rings for, I guess, since 2008 is when I started at Tennessee. Yeah, I love the broad application of dendrochronology. You can date old houses. We've dated historical instruments. You can study the climate, ecology, carbon. So it's such a very, like geography, it's very broad in its applications.
Yeah. And this is something that I think a lot of people, students, are aware of the concept of a tree ring. You see that at nature museums and preserves and things like that. And unfortunately, it seems like very often the takeaway for folks is, oh, you can see how old a tree is, but there's so much more depth. Why don't you tell me one of the crazy side effects, oddball things that you can tell from tree rings that maybe an average person doesn't know about?
Let's see. So one of the neatest applications of dendrochronology that I've seen is researches that go back to Civil War battlefield sites, and they actually use CT scanners to scan the trunks of the trees that still exist because they were growing back in the 1850s, 1860s when you had the American Civil War, and study the battle through the intrusion of bullets into trees. And you actually date when the bullet went in, and they have a pretty good idea when that battle happened. But that was one of the crazier applications of dendrochronology that I've heard of. I haven't done it personally, but I'm always surprised to kind of pull it back to something I've been involved in. Because I'm currently involved in a project where we're excavating unmarked graves in Jackson, Mississippi. So it's at the site of the current University of Mississippi Medical Center in Jackson. It's the only research hospital in the state. So it services a huge area, mainly rural population. They're really the only green space on their campus left. They went to build a parking garage or a building or something like that. And of course, they did the pre-surveys. They found 7,000 pine boxes, right? 7,000 unmarked graves. And so we're a really small portion in that huge research project with a lot of bioarchaeology, people actually exhuming bones and studying who these people were. And so, yeah, that's probably the oddest, kind of unintended project that I'm involved in.
So those pine boxes, then, are they looking to try to age those pine boxes from the growth patterns?
Right. And so they have a pretty good idea of the dates of the cemeteries with written records, but they have no idea of the individual graves because they're unmarked. They basically were past patients at the hospital that passed away and maybe didn't have any family. And so they just put them in a pine box and put them in the ground with no marker. And yeah, so the archaeologists are excavating the pine boards and they're sending them to us or our lab here. And we can date when those trees were cut and then most likely immediately used in the construction of those pine boxes.
Mm-hmm. Well, I think I'm going to come back to this and try to learn from you how you date those boxes. But maybe this is where we talk a little bit about the whole process of evaluating tree rings in the first place. So what does it look like? How do you, let's just take a simple example of a standing living tree. How would you go about assessing that tree?
The first thing to think about is we have a couple of like theorems or principles in dendrochronology, or arguably the most important is site selection. So it really matters where you select your trees to try to address whatever question you're asking, right? And so if I'm looking to use some trees to look at their tree rings to reconstruct temperature, I'm probably not going to go to Florida because those trees aren't really limited by temperature because temperature is really nice and it doesn't really get cold. I'm probably going to go to like really high elevation sites or high latitude sites where you have trees that are like actually limited by temperature. And that's the first thing is you ask yourself, what am I trying to address? If you're looking to look at drought, you need to go to a dry area because those trees are going to be sensitive to the amount of rainfall, not the tropics, right? And so where in the region or environment really dictates what those trees are going to be able to tell you about the environment.
So taking that drought example, so just to maybe not put too fine of a point on it, but if you have a drought adapted tree, when you do get periods of substantial rain, you may see more growth, for example, than in a more typical dry period. And then if it is exceptionally dry, it'll be even less. Like, is that kind of what you're looking at?
Right. And so that for kind of drought analyses or a drought project, we will go to like the American Southwest, for example, is a phenomenal area around the globe where you have trees that are like just barely hanging on to the margins of life and they're limited by moisture, right? How much rainfall they get. And so they're in a really heavy monsoon summertime, for instance, the North American monsoon, that ring will be really wide. And if the monsoon fails and they don't get much monsoon rainfall, the ring's gonna be really narrow. Or if there's 10 years of monsoon failure, 10 really narrow rings, or honestly, trees might miss a ring. It's called a locally absent ring. And so to kind of arc back to what you asked before, like if you have a tree, what do? Well, when we core into it, what the tree didn't form the ring right in the spot where you core it with a little handheld borer, you missed that year. And the crux of dendrochronology, because it's it's actually a sub-annual science. If you're off 1 year, you're completely wrong because it's a chronosequence. And so it's highly important, obviously, to make sure that every ring has the correct calendar year assigned to it.
Hey, nature enthusiast, do you want to be part of something bigger? Well, we're building a movement at Jumpstart Nature, and we've just added some new volunteers to help with our podcast and website. But this means our costs are going up too. I need to purchase software licenses to give them access to the production tools we use. For example, one media editing license costs $21 a month. And this is where you come in. Please consider supporting our mission by contributing to Jumpstart Nature through our Patreon or direct contributions, or even purchasing some logo merch. Check out all these options at jumpstartnature.com/donate, also linked in the show notes. Not ready to make a financial contribution? Then please share this episode with 3 friends. Sharing what we do is actually one of the very best ways you can help us. Thank you all for your continued support. And you started to say, like, I think another maybe misunderstanding a lot of people have, because you go again to these nature centers and you see like entire stumps that have been cut. That's not what you're doing necessarily, right? You're using a special tool.
Yeah, we're using a special tool. It's about, if you can imagine like a drill bit, everyone can picture like a handheld drill, like a DeWalt drill or whatever, and a drill bit. But the drill bit is hollow inside. And so when you turn it with your hand, it pulls itself into the tree and it extracts like about a pencil-sized piece of wood that has a signature, the pattern, the rings on it. And that's just a really nice way to acquire all the rings of a tree to the tree's life without cutting it down and killing it. And a lot of trees have defenses against, poking a hole into it, because that's a really common question. Like, well, you're poking holes on trees. And so there's a lot of studies that go back to previously sampled trees and analyze the health of the trees and how those trees have defended against the hole we poke into it. So yeah, there is a little bit of damage, but it's localized, and it allows us to see the trees without killing, or the rings without killing the tree.
Mm-hmm. And this, you called it a chronosequence?
Yeah, a chronosequence in terms of, if you can kind of imagine, everyone's seen a cut stump of a tree. The very center of that cut stump is called the pith, Pith. That's basically when the tree was a little tiny seedling. And then every year, in a concentric fashion, it put on a volume of wood around that seedling. And as that tree kind of grew and the trunk got bigger and wider. And that's what we look for and sample.
And this is maybe like more of a left field kind of question, but are there any trees that show more than one ring per year? Like they have two different growth cycles within a given calendar year?
Totally. That's a really good question, and a really good thing that a lot of people should understand. Dendrochronology doesn't work everywhere, right? And this might be jumping ahead a little bit, but we probably arc back to it when we get to the paleoclimate aspect, right? There are a lot of different proxy indicators, we call them proxies, because these are natural archives of environmental change or climate change that exist in natural objects around the world, right? Like cave stalagmites, fish ear bones, ice cores, lake sediments, tree rings, corals, right? If you're looking to say anything about the ocean, you can use trees because there is a teleconnection there with the environment, but you better get in the ocean and look at clambrose, odorless corals. And so to answer your question, there are trees that form multiple rings per year. Mainly they exist in the tropics, which is kind of an area it's kind of a frontier for the science of dendrochronology. Some species work in the tropics, most don't. And if you can't establish as a dendrochronology, if you can't say that this tree forms consistently annual rings, then it's not useful, right? So if that tree's forming one ring this year, and then two next year, and then one the next year, and then three, you can't use that as a chronology.
Yeah, that makes sense. And I'm also thinking back to what you were saying with some of these drought adapted trees where there may not even be a tree ring in a given year. So that leads me just to the conclusion that you must have to sample a fair number of trees and species to cross-reference to each other.
Totally. That's why it's super important. If I were to go and pick a study site or a forest to grab tree rings from, we would core 25 to 30 trees. And so the number of samples, the number of trees we get is usually around that number. Any more than that, you're not really adding much more to your data set. But we certainly need to have enough so that we're not missing any rings. It's kind of like all statistics of trying to get a good sample population.
That makes sense. As we were talking, at the beginning too, there's just so many exceptions to everything. I can only imagine too that all the background knowledge you have to select the site and get that sample of different growth patterns for different trees. And then you have microclimates and you have all these other things you have to account for in this. I skipped ahead. So I want to go back to the borer. When you bore out this core, then how do you go about looking at it and assessing it? What's kind of the next step there?
So the next step is, we'll go into the forest and use our little handheld increment borers to extract pencil-sized piece of wood from trees. We usually immediately put those in paper straws. I like to look at it as we extract it from the board to see what the tree rings look like. You can automatically tell, especially if you're coring a pine tree and you actually see the rings in the piece of wood. You can tell how old it is or an estimation of how old it is, but we immediately put it in a paper straw. That paper straw helps to kind of dry the core out so that when we get back to the lab, we take those cores out of the straws, we mount them in these special channelized wood structures that they're called core mounts, where we glue those in there to help stabilize the core. We then sand it down using just regular sandpaper. And what that does is it kind of puts a nice polish on the surface of the core so you can exactly see the rings under a microscope. And then we measure them, and then called cross dating is the final form in creating a data set from tree rings.
And when you're looking at these and measuring these, so this question is going to be totally skewed because about a month ago, I was up at the ancient bristlecone pine forest.
Nice. Yeah. White Mountains. Yeah.
In the White Mountains. Exactly. And there was a ranger there that showed the increment borer and talked a little bit about how it worked. And they had a nice video in the visitor center as well. And one of the things they said there was that some of these rings are so small that you're like having to look through microscopes to make these assessments. So, okay, you have microscope in your tool bank. What else do you have to do to really inspect these?
Yes. And you kind of touched on a crux actually in the science of, we have microscopes here in my lab here at Idaho. But so the old way of measuring tree rings was on this really high precision measurement stage where you turned a little wheel and it just at a micro, like a thousands of a millimeter increment just moved. And there was a little button you would press every ring when the crosshair in your reticle got to every ring. And so you kind of manually had to measure every ring. So imagine like you're measuring 5,000 years of bristlecone. It would take you like 4 days, right? Now we have these super high resolution cameras, and just Nikon or Canon cameras that are calibrated. They're specially calibrated to our little photography stage. We just take a scanned image at like 40,000 DPI, and that gives us a digital image that we pull into a computer software, and I can drag a path with my cursor all along the axis of the core, and then the special software just measures the rings for me. It takes a fraction of the time. The technology has advanced a lot.
Yeah, well, okay. And that probably answers some questions I had coming, because I'm thinking about, 5,000 rings in a few foot length of a core is pretty crazy. But then I'm guessing that same software can help give you some assessment of the width of the rings and point out anomalies or things that maybe are of interest to whatever question you have that you're looking to answer.
Totally. Yeah. And not just the width of the ring, I mentioned earlier, it's a subannual or can be a subannual science. We've got now to measuring the early wood portion of a ring and the late wood portion of a ring, as we call it. And just for audience who don't know what that means, the early wood portion, everyone knows again, go back to the cut stump, that light colored band or the white band that goes around, that's the early wood portion. Those are cells that are formed by the tree early on in the growing season. And as that tree progresses to the summertime, it starts to slow down its growth. And it starts to form the same type of cells, but the cells are really small and they have really thick cell walls. And so that color kind of changes to the darker band. And so the early wood light band plus the late wood dark band is one annual ring. Over the past 10, 20 years, I've realized that, oh my goodness, season wood widths can be more accurate at saying something about the climate than total ring width. And so we might just measure the early wood or late wood because they can more accurately say something about more seasonal subannual climate.
Yeah, that's really interesting because you're getting a running within the year, you're getting kind of a running point of view of what's happening.
Totally.
And the other thing I think that really stood out to me from and by the way, for anyone who's not seen the ancient bristlecone pines, I'm certain I've mentioned it on the podcast once or twice before. Number one, if you have the chance, do it. But number two, these are the oldest living things on Earth as we understand it right now. Just to explain what's so special about them.
Did the ranger kind of point in the general direction of Methuselah, or what they call Methuselah?
No, but so this was part of a field ecology class that I sometimes help out with, and the professor knew the general direction. But yeah, we didn't see Methuselah, but there were definitely, even on the little nature walk that we did there, definitely some very old trees, easily 2,000 years old along that walk. And yeah, that's the tip of the iceberg.
And I don't want to take us off. We can come back or not go down this road, but like the story of Donald Curry. I don't know if they mentioned Donald Curry while you're there. It's an amazing story.
Was he the University of Arizona kind of founder of dendrochronology?
No, so that was A.E. Douglas. So Don Curry was a graduate student. I'm blanking on exactly where he was a grad student, but he was basically given permission by the Forest Service. Again, blanking on the decade of this was, I think 50s or 60s. He cored the bristlecone pines and got his borer stuck in the tree, right? One borer. So he got special permission from the Forest Service to cut it down. And then after he cut it down, he realized after cross-stitching the tree that at that time, because this is before they found Methuselah tree, that was the oldest non-clonal tree in the world. And he cut it down. And so he got the name Killer Curry, just colloquially. But we actually went on to have a really amazing career at University of, I think it was at North Carolina, but in another field. But yeah, I just can't imagine that feeling of at that time thinking you cut down the oldest thing in the world.
Well, okay, and I'll drop the bristlecone pines here after this, but one of the things they have in the visitor center is a timeline, and it's based on Methuselah. So Methuselah is thought to be the oldest of these bristlecone pines, and I can't even remember. It's close to 5,000 years old, I believe. So on this timeline, you see all the things that have transpired over the 5,000 years, and they just get more and more amazing. Like the invention of paper is like 200 AD or something, and then you go back and King Tut born, and then the pyramids of Giza, like it's older than all of these things, and it blows your mind to see it.
It's pretty sobering, right? It's like one of the amazing things. I think that tree has been rooted in the same place for all those years, and again, like you've experienced walking through those ancient trees, it's pretty sobering to do that.
Yeah, thinking about what that means, and I purposely word that vaguely. Okay, where were we? I was talking about how many rings there are and how difficult it is. And that's leading up to the fact that when you're looking at old trees, there's a lot of uncertainties about how they've grown and what the growth pattern is. And you might have multiple stalks that have fused together, or the interior might be hollowed out and rotting like a lot of oak trees. So when you're getting down to like, okay, I know this is the site that I want to bore at, then do you have a special eye for picking out the best tree?
There's some pretty good research that's published in papers that kind of identify what's called like old age architecture. And so there's certain kind of characteristics that mainly trees, I'm thinking of conifer trees, any pine tree, that they take on when they get really, really old. So obviously one is like really large trunk. But that's one of the most common misconceptions is, oh, it's a large tree, it's really old. That sometimes is the case, but most time not. Really large lower limb. So there's a certain kind of architecture that these trees take on where I can kind of look at it now having cored thousands of trees and go, oh, yeah, that's probably pretty old, or no, that's not really old at all. Mainly I get contacted by people who have a really large tree in their yard and they think it's like 500 years old. I'm like, nah, it's probably 40 years old, because when you think about environment, trees growing in their yard, it's probably irrigated. It's got no competition. It might be fertilized. Gosh, some of the oldest trees I've cored are just tiny, no bigger than someone's arm, but they just kind of suppressed under the canopy of trees and just kind of hang out there with really low light. So you never can tell. Yeah,
that's really interesting. And you think about like growth strategies in general, you do see a lot of animals that grow really fast have shorter lifespans too.
Exactly.
So now, okay, you've extracted a core and you have some nice software and cameras to help you with your work now. I'm glad that's the case. Otherwise, there's probably some people losing their minds after a while.
Right. And their eyes.
Yeah, their eyes. So I know there's lots of things then that you can infer beyond the weather conditions and the growth. Weather conditions is an inference already, because you're really just looking at the growth rates and then making some assumptions. But what else are you looking for in these rings that give you some indication of the ecological history of that area?
So let's say we're in the eastern U.S., like an eastern deciduous forest. It's really common in the eastern U.S. You have, compared to the west U.S., in the east, you've got really thick, generally higher biodiversity with regard to different types of tree species you have. So you have a lot more competition, right? And so the ring patterns in those trees are going to be probably more dictated to competition than they might be for climate. Kind of the opposite in the west, where you have more spaces between trees, less competition. So you have less of that ecological signal and you have more of a climate signal. And so it really can get tricky, especially if you're kind of working in the east, to try to find trees that have the least amount of ecological signal and the most amount of climate signal. If your goal is to do something with climate, if you're an ecologist and you want to use kind of tree rings as a tool to answer some kind of question about community ecology, then yeah, you probably want to go to the east and you want that ecological signal in those trees that you core. So again, going back to site selection, it really kind of depends on what you're looking for. And again, knowing, the actual phrase is called your signal to noise ratio. And so based on your question, you kind of want to minimize that noise that would otherwise interfere with your signal that you're looking for, and do that by choosing your trees carefully.
Yeah. And I think that really drew it together nicely for me was you talked about some of your oldest trees or the smaller ones because maybe they were enshrouded by a canopy and didn't have optimal growth conditions. So that limiting factor there is light, not climate. And I think that's, at least in my mind, a really good example of what you're talking about.
Totally.
So one of the things that I also found really interesting is, we're talking about coring living trees. And as I understand it, you can actually go deeper in time. So you can already go pretty deep, at least in one location with those ancient bristlecone pines. But I know there are some other techniques you can get even into deeper time through these methods. Can you tell me a little bit about how that is achieved?
Sure. Yeah. The primary method is called cross dating, and it's one of the foundational aspects or principles of the science. Without cross dating, we really don't have a proxy or a science. Real quick tangent, I'll get back to the question, but the actual process of crossing has actually bled its way into matching up the patterns in bands of stalagmite growths. Same thing with corals. And so that process of kind of matching the patterns of their growth bands or rings is super important in kind of weaving together the stories that like 50 different individual trees tell in the same forest, right? So it's kind of averaging many different trees to better understand how they're growing, through their lifetime. And so that's the first thing we do. If you think of like crossing like a barcode, it's basically matching barcodes, right? Like every core I pull out of a tree has a certain pattern of rings, and that basically looks like a barcode that you would see in whatever product you might buy. And so if you can picture 50 barcodes that aren't exactly the same, because all different trees are individual biological organisms, they're not going to have the same growth rate, but they're going to be responding in a similar fashion to the environment in any given year, right? And again, it's in those certain environments where the trees are doing wildly different things where the science really doesn't work. But other than those really rare occurrences, trees are going to be responding in a similar fashion. You can then match up those barcodes to create a chronology. It's just an average chronology of growth for as long as your living trees have lived for in your given area. Now, if you want to extend back in time, like you said, we look for dead trees, look for remnant stumps or logs on the ground. We can actually get into old cabins or structures and collect that material and again, cross date that to extend our chronologies back in time.
Interesting. So you could find a cabin that some frontiers person built in 1700 and take a core of the wood that they used to.
Totally. Yeah. And if you think like, come across an old cabin in the woods that, at some point, some person in the past cut down those trees and they used them to build that structure. We have no idea when they cut down those trees, and hence we have no idea when those rings were formed. But what it requires is what's called a reference chronology. So it requires you to have a chronology already in place in that area that's going to have the same signal as, the material in the cabin. And again, that's where the barcode matching comes into place, as we match the barcodes of the cabin trees with our reference trees and hopefully extend that chronology back in time. And usually that's the case.
Again, you've added so much more nuance here, because I've always imagined this, like you have your rings lined up in maybe two parallel rows and you're moving one until you get that nice match where the widths are all the same, but then it's even more complicated because the tree on top that you're comparing to the tree on the bottom, maybe it was growing in a more mesic area or some other aspect about it. So it won't be the same widths necessarily. It's the same kind of fingerprint almost. So yeah, very challenging. And I can see where software can be helpful.
Right. And you really hit the nail on the head in that. It's a really nice description. What we really look for are called marker rings. And so marker rings are those rings that they're anomalies, right? They're just really kind of rare, maybe one every 10 years, really anomalously narrow rings, or honestly, really wide rings can be marker rings as well. And then again, that go back to like the mechanism, what's controlling those marker rings is just going to be just extreme environmental or climate conditions. It's going to impact all the trees in that area, not just one or two, but all the trees, because it's a huge effect on the forest. And that's what we use to really match up those patterns, is looking at those marker rings. And again, if one core from a tree is off by 1 year, we can tell that, and we can, that helps us identify if that tree might be missing a year. So it helps us with cross-sitting and matching up those patterns.
So then circling back to those pine boxes, you have basically planks or boards at that point. It's not like a full core. Is the process still kind of the same? It's just you have a smaller cross section to work with?
Right. So if you can imagine, like, when they would fell a tree back in the day, they would rip lengthwise the pine tree, these would happen to be, to create coffin planks or boards. And so we really only have like a spline, a portion of the trunk. And so we really can only date the pine boards that have like the outermost growth here, and a lot of these still have bark attached. That lets us know that that's the absolute outermost ring, the death year, if you will, of that tree. And that tells us when that tree was cut down. And we have like lumber records, timber sales back in the late 1800s. And so we kind of match up what the trees are telling us with the written records to date each individual grave. They actually have a list of people who died in that hospital. So they're trying to match the dates that we give them with their candidate list to do the best they can at identifying whose bones these are.
Yeah, and then I guess it's a similar process then for other plank structures, so to speak, whether it's an ocean vessel or a structure or whatever the case might be, or
a musical instrument. One of the coolest projects we've done recently was a music professor here at the university heard that there's a new dendrochronologist in town when I first got hired, and so he showed up with this huge stand-up bass that ended up being older than he thought, and so the maker changed, and it's like now worth a lot more money. Back when I was at Tennessee, we actually dated a Stradivari violin and kind of confirmed that it was Stradivarius, which is probably the most expensive thing I've worked on, because that thing was like $5 million.
And they let you take a core out of it?
No, so the musical instrument is a little bit different. So that most instruments are like kind of butterflied from like one piece of wood. And so we just kind of took it and put it on we have a flatbed scanner and like a paper scanner. We just like scanned it at high resolution. It's a little more than a paper scanner, but just for people's minds, picture a big paper scanner, and we scanned it at high resolution and dated it without hurting it. There were a team of people in really nice suits that were there to protect it. So it's pretty intimidating.
Yeah, I guess you don't know what's going to pop up in your email box any given day. Some crazy request.
Exactly.
I want to get into a little bit more of the climatology and wildfire side of all of this. And, I've heard that you can infer some things about fire return intervals or average fire behavior in an area. What does that look like? What are you looking for to come to some of those conclusions?
So it looks totally different than what we've been talking about up to this point. And so it's a large portion of my research program here. I love studying fire through tree rings. It's dendrochronology. So dendro, tree, pyro. And so essentially we're looking for scars that are caused by a wildfire that burns through the forest. It basically scars or kills a portion of what's called the cambium of a tree. And so without going too much in the weeds, the cambium is like the only living portion of the trunk of the tree. It's a really thin layer of cells right inside the bark. And so if you have a fire that burns through, it's going to kill a little bit of that cambium, and that, just like, if you were to cut your arm, you have a scar from your skin healing over, right? The tree kind of heals over that scar or that burn. It leaves evidence of a past fire. And so we look for trees that have, 15, 30 fire scars on them, because again, that's direct evidence that a fire burned through the forest. We can look for changes in frequency of fire activity through time.
And it also, I think, probably it must give you some, through selection bias, I suppose, some indication of the severity of those fires.
Yeah. So the sampling design is really interesting with fire history. There's a couple of different ways that you can implement that type of research. I tend to go more of a targeted sample design, where I go through the forest and we actually look for what's called a cat face, which is like a very specific dendro term. But basically, it's this really triangle shaped portion of a tree trunk. It's at the very base where recurrent fire has opened a wound and kept that wound open. Because if you have one fire that kind of wounds a tree, that tree is going to heal over itself. If there's no more fire, you're not going to be able to see it. It's going to be buried inside the trunk as the tree grows out, and older. But if you have a lot of fire, maybe a fire every 3 to 5 years, that wound's going to be open, and you're going to be able to like take a chainsaw and cut a small portion of that trunk away. So the sampling technique is different. We don't really use increment bores for that because it's very difficult to core a tree and get the fire scars that you're looking for. So we're kind of required to take a chainsaw and remove, a very, very small portion that just has the fire scars. They're a little bit different, but as effective.
So I'm trying to wrap my head around what this looks like because I think I've seen what you're talking about before. And where my mind got a little bit lost was, okay, there's some minor damage and the tree can repair itself. In this case, there's not really that same opportunity to repair itself. So how are you able to assess the number of fires or the return interval of those fires in this case if you don't see that new growth, the attempt at repair, essentially?
Right. Well, and then that's why we're required to take, with a chainsaw, we can remove what's called a partial cross section. So it's anywhere from 10 to at most 25% of the trunk. So like kind of like a pie slice almost. We tend to go really, really thin. Again, that sample that we remove, that little pie slice, is going to contain all those growth curls or those fire scars. So we can actually see where those scars started in the trunk.
Okay, I think I got it. The geometry of it makes sense. So it's like along the one edge of the pie piece where the tree is repairing itself, that you're able to see this. Is that it's hard to explain without drawing it.
I know it or showing it. Yeah, it's really difficult to kind of visualize. But yeah, and if anyone's listening that's familiar with like chainsaw use, it requires us to take like lateral cuts and plunge cuts. Mm-hmm. So it is a little dangerous. We have to take training from the Forest Service. You have to have your certification basically to operate a chainsaw because it is arguably the most dangerous part of the science is operating a chainsaw. But it's really the only way to acquire that fire information from a tree.
And I don't know if this will work or not, but do you have a photograph of one of these cuts that maybe would, for anyone who wants to see a visual, I could include in the show notes?
Absolutely. Yeah. I can send you a really nice example of a kind of a fire scarred partial cross section.
So do you have any observations or anecdotes from this work that you've done in looking at fire history that are surprising? I think to answer that, we probably also have to understand what you were looking for and where you were looking.
Yeah, I think the main take home message, which I think, again, like any viewers in the West, they're going to know this already without me telling them, our forests are in trouble. Basically, we have suppressed fire for 70, 80 years. The active process of land management was to see a fire, put it out, right? Even though that fire might be natural, as we kind of population grew and that's understandable, right? You can't have a wildfire that kills a bunch of people. So in doing that, we've essentially allowed the forest to build up a bunch of material. And that's kind of what everyone's seeing every year is wildfires that are out of control. Again, I'm not pointing the blame at anybody. It's a natural factor of a growing society. But, that's kind of why our wildfires are out of control now. In addition to being worsened by dry conditions, really hot temperatures.
This may be too much of a leading question, but I have an impression that some of this research revealed a much higher, I'll say quote unquote natural, because there could have been, that's a thorny definition in and of itself, but a higher frequency of fires historically than maybe people realize. Is that roughly accurate, or is that aligned with what your research has shown?
Yeah, it directly aligns with it. Honestly, across any portion of the U.S., there's been fire suppression for about 80, 90 years. What we see is really frequent fire. We're just now about to publish a study out of Yellowstone National Park where we have constructed a fire record with tree rings, an annual fire record back to 280. And so it's about an 1,800 year long record. It's a really long record of fire. And there's about a 5-year fire return interval in this area up until like 1900 and then nothing. When you have about 100 years of no fire in an area that has seen a fire every 5 years or 7 years for 1,700 years, you're going to have a problem.
Yeah, that's for sure. And I think that's the thing too. It's just, there's going to be this psychological impediment, I think, that we have, because I think we're so used to seeing fires as these huge, immense, out of control, like canopy fires. And presumably these more frequent fires were quicker and less thorough in their destruction at that point.
The Smokey Bear campaign was a really successful campaign. I think it's considered like the most successful marketing campaign in history, which obviously you need to happen, right? You can't have people going out and setting fires. But again, it got people, I think in general, thinking fire is bad. Fire is not needed in this ecosystem or these ecosystems in the West when it actually depends on it. Mm-hmm. But again, touchy subject.
Yeah. Oh yeah. There's so much more depth to that I hope to do a Jumpstart Nature podcast on that actually. So maybe then getting a little more into the climate side, I did have a listener. So I asked my Patreon supporters if they have any questions in the topic that we're coming up with. And I think this serves as a good transition. And they were wondering, what can we infer about carbon sequestration from tree rings?
Yeah. So quite a lot. So, to kind of talk about the basics of how we can tell, kind of carbon allocation for a tree. So you can tell with the tree rings, or you can kind of trace it chemically. And so if you think of like the process of photosynthesis and respiration, in that process or those processes, trees actually act as a carbon sink. They have the ability to store more carbon than they release in the atmosphere via respiration. And so you can kind of get an idea of carbon allocation and carbon sequestration, how much trees are pulling out of the atmosphere by looking at those growth rings. And then chemically, you can trace it with what we call isotopes, which is a small atom that leads a signature of different elements that are involved in that process. And so the most two common isotopes that we can essentially measure through a ring sequence or a core are carbon and hydrogen. So carbon can kind of tell you about the amount of carbon the tree kind of sucked up and allocated, locked in its wood. Hydrogen tells you more about like the amount of water, the type of water that was involved. Yeah, it's a little expensive. The main point I was going to say is it's a kind of a burgeoning or a frontier area of the science of dendrochronology that people are now starting to realize that we can create carbon sequestration models from not looking at like, again, I think the challenge is you need a lot of trees. And so there's actually a big push to use what's called the Forest Inventory Analysis Program, the FIA, which is a lot of tree cores across the globe, mainly the US, to construct these models that can be scaled up to the globe.
And again, I think like every tree probably has different behaviors too, in terms of how much carbon is shunted to the root system versus retained in the, in the shoots and limbs and stuff.
And it matters how old the tree is. So the age is a dependent, the species, yeah, it's a really important, interesting area of the science.
You've already hit on some aspects of how dendrochronology can help us understand historical climate just based on looking at these growth patterns. And then I'm imagining a big database of all these assessments that have happened in suitable locations around the world. So you can see, okay, this wasn't just a California thing, or it wasn't just a Maine thing, or, whatever the case might be. Very open question, but like, how does dendrochronology itself help us understand historical climate?
The main process would be to, again, go back to that principle of site selection. There's another principle called the principle of limiting factors that I touched on. I didn't really name it by name, but it's essentially the job of a dendrochronologist to analyzing how your tree rings are correlating with instrumental data. You can kind of tease out what's the limiting factor in terms of how, all the different metrics we measure. We measure precipitation and temperature and vapor pressure deficit, all these things, right? We have a host of weather and climate metrics that we have been collecting for in the US, but 120 years. And so we can actually build a mathematical model between the tree rings of the past 120 years and actual instrumental data. Based on the strength of that model, we can then infer that past ring widths are an estimate of this much rainfall or this much temperature, right? So it's kind of calibrating the modern tree rings and extrapolating and reconstructing estimates of past conditions based on what the ring sequence is, right? And based on how old your trees are, tells you how far back in time you're able to go.
That makes a lot of sense because, yeah, we have 120 years of pretty good concrete data that can be cross-referenced. And I guess that also leads into another question is, I know people are looking, say, at ice cores and looking at some of the other things that you mentioned. Is there a cross-reference between these other, I'm going to call it deep time. It's not really that deep time, but deeper time measurements or assessments?
Yeah, there are ways you can use what are called like multiple proxies. So there are these really complex mathematical models where you can like use ice cores and lake sediments and tree rings to calibrate them together to reconstruct climate. Is that kind of what you mean?
Yeah, yeah. Like if you take the principle or the idea that we don't know what we don't know, like maybe somehow something is different once we get beyond those 120 years. And if you can cross-reference what, say, your tree rings are telling you versus what the lake sediment is telling you to say, okay, I feel more confident now that we're on the right path.
Exactly. And that's a really good clarification. So I actually use, in any kind of like climate reconstruction that I perform, I do look in that area for other proxy reconstructions of similar climate metrics. And the example I use is the Yellowstone. We actually reconstructed snowpack to go along with our fire record. And I got on the NOAA website. There's a huge paleoclimate repository of past studies. You can publicly available data. I downloaded a lake sediment reconstruction of drought from a nearby lake and use that to validate what we're seeing, right? Because if I'm seeing something totally different, maybe I'm wrong, maybe they're wrong, who knows? That kind of is an interesting point. But you're looking for corroboration or validation or an assurance that you're on the right track with your reconstruction. Because again, they're just estimates, right, of past conditions.
Yeah, another kind of, in retrospect, maybe obvious light bulb just went off in my head, and that's along the Sierra Nevadas and the Cascades, there are still glaciers. So there are actually, I presumably there are ice cores from those glaciers that can help you see what the historical snowfalls were, and yeah.
Yeah, I mean, especially in temperature as well. Like we've been conducting a really extensive sampling collection effort from Mount Baker all the way down to, we just got back from Sequoia National Park and like the Southern Sierra to collect tree cores for temperature reconstructions along the West Coast or the Western US. And yeah, we're absolutely going into ice patch, ice core, those glacier records to see what they are telling us, how they match up with our reconstruction of temperature.
And I was hearing just recently, I'm sure you know all about this, but you're talking about sedimentation, which is also an indirect indicator of runoff. There's just so much you can piece together with all these different data points.
Absolutely.
And this is a case of where I don't know what I don't know, but what interesting conclusions that you've been able to find from, looking at the climate record in this way.
Definitely. So in any kind of like paleoclimate study that we're doing in my lab specifically, because that's what I'm interested in, is we're using trees to try to get back to at least 2,000 years, really. 2,000 years will give us a really good characterization of what's called the medieval climatic anomaly. And that was, other than current time period, the most recent event of just really warm temperatures, specifically in the Northern Hemisphere. And so if we can compare current temperature and drought to what was occurring during the MCA, or the medieval climatic anomaly, that was about 800 to 11 or 1200 AD, in that kind of portion of history. Then we can kind of assess, are current conditions anomalous? Was it warmer or drier back when we weren't pumping up oil and emitting greenhouse gases, right? And obviously affecting the climate. That's a really important benchmark in terms of paleoclimatic analyses, is comparing current conditions to what happened 800 to 1200 AD during the MCA, and then kind of how that transitioned into the Little Ice Age. Because again, this was before humans were impacting the climate on a major way. And so by studying what is more natural changes in conditions from like really warm, really dry MCA to really cold Little Ice Age, we can better understand like the variability, the rate of change that our climate naturally goes through.
What challenges might you face when trying to reconstruct climate data from tree rings?
So I think the main challenge is making sure you have accurate instrumental data, right? So again, if you don't have any instrumental data, what are you going to use as your calibration model or your benchmark that you use to reconstruct back in time? So if you're in an area across the globe with like really sparse or inaccurate instrumental data, then that really limits you with regard to your kind of reconstruction or paleoclimate power. And so, yeah, we obviously have those regions across the globe where we need more instrumental data that will better inform not only our past paleoclimate reconstructions, but our future forward models of climate, right? So that, and again, in focusing on the U.S., areas that have inaccurate data, again, you're kind of hamstrung and limited. Mm-hmm. But that's, I think, probably the biggest challenge.
All right. Well, I know we only scratched the surface, or maybe scratched the cambium layer. So if people want to dig in a little bit deeper into dendrochronology and learn a little bit more, do you have any books or maybe YouTube videos or anything else that you might point them towards?
Totally. And I love that question. There's a whole host of areas I can kind of point you to, and just real quick, to kind of touch on the highlights. The major book, it's I think available on Amazon for fairly inexpensive. It's called Fundamentals of Tree Ring Research by James Spear. So Jim Spear is a professor at Indiana State University. If you look him up on Google, you'll find his book. It's a really good kind of written for just a general audience. So it's less jargon. It's great. YouTube, there's been a lot of YouTube videos that have been popping up over the past 5-6 years. How to cord trees. So you can get demos on anything nowadays on YouTube, especially within the world of dendro. And then we actually have a dendrochronology science camp where you can come and learn about tree rings. So it's called the North American Dendro Ecological Field Week. And it's a mouthful. It's NADEF, so NADEF. If you Google search that, we have a web page. It's a little expensive. It's like $1,500 or so. We kind of changed the location of this field week depending on the year. So we just had it a month ago in on the shore of Lake Tahoe, which was absolutely amazing. It's just 50 students, professionals come together. Everything's included. You take a project from A to Z, and you leave there being able to construct your own dendro projects. Yeah, that, and I like Science Twitter a lot, or Science X, whatever it's called now. Seeing papers that people put off on there is pretty good. So follow some dendrochronologists on X.
Well, yeah, thank you for that. I'll include links where I can to those resources too in the show notes, as always. And yeah, from what you have an interesting perspective. I think your field has an interesting perspective because you're looking at time in a different way, I think, than most people do. So again, maybe I'm leading into this question too much, but if you could magically impart some ecological concept to help the general public see the world as you see it, what might that be?
One of my favorite ecological concepts is the abundance center hypothesis. It kind of feeds into some of the work that we're doing now, but I won't get into that. But essentially, if you apply this hypothesis to tree species, it basically says that like trees that are in the center of their geographic range are going to have a different kind of life than trees that are on the very margins of the range, right? Where you expect to find that species or not. And so it's at those margins that we're seeing a lot of change now in migration in a host of species. So yeah, so it's a better understanding how the ranges of plant species might change with impending current impending climate change, I think is just super important. And not only for like natural systems, but if you, again, probably not part of this podcast, but like if you study how like agriculture, right, of where it might be suitable to grow a certain type of crop in 50 years as opposed to now, super important for our food system as well.
Yeah, interesting. It makes sense. And it's, again, like so many good concepts, it takes something that makes sense and makes it clear and on the forefront of your mind. So do you have any upcoming projects or anything that you'd like to highlight?
Sure. Yeah. So we are working on probably the biggest project that I can think of is the North American Temperature Atlas. And listeners might be familiar with the North American Drought Atlas. It's a gridded drought reconstruction product where you can go to any location and better understand the drought history of that area. Well, we want to do the same thing, but for temperature. And so we're working on this North American Temperature Atlas to compare with the Drought Atlas, where anyone can go and look interesting findings that we have recently come across. Again, like I mentioned, we're doing temperature reconstructions across the entire U.S. The one place that we found where current temperatures are cooler than in the past is the Southeast US. So it's kind of this warming hole, if you will, of, it was warmer back in the 1800s than it was now, as suggested by our records. And so that's really interesting because that's the only place where we found that to be true. We think it's because there's been a lot more trees being planted and grown there so that the forestation is really high there. That might be cooling off that area. That's a really interesting kind of project that we're currently delving into.
Yeah, very interesting initial insight. And then also anything with Atlas in the name kind of has me right away. I'm going to be interested to follow along with that. If people do want to follow you, your progress on this project, or you personally on social media or webpage, whatever, where should people go?
Yeah, that'd be great. So I am on X, or what used to be called Twitter. So my handle is at dendrotrog, as in like dendro tree, trog, cave. And I'm pretty active on X. I really only focus on like science-based stuff, nothing else. So if you're interested in dendrochronology, follow me, follow the people that I converse with, and I'm friends with a whole host of people on there. So that'd be a good place to find me.
All right. Sounds good. And then one other shout out, and I don't know, I think I mentioned this earlier, but if it doesn't make the cut, back to resources where people can learn more. And this isn't going to necessarily be super deep learning, but definitely very entertaining learning, is you were on the Radiolab podcast this past summer talking about some of your work in a very interesting way. So I'll make sure to link to that as well.
That'd be great. I appreciate it.
All right. Well, thank you so much for getting into such a broad topic and putting up with some at times vague and open-ended questions for me. It's been a very educational experience. So thank you for that. I appreciate the work that you're doing and continue to do.
I very much appreciate your interest, Michael. That's awesome to be a part of this, whatever episode this ends up being. So I also appreciate the work you're doing. So thank you very much.
Thanks for sticking through the entire episode. If you made it this far, I hope that it means that you enjoyed it. If so, please spread the word and share this episode with 3 friends or groups that you think would enjoy it too. As for today's episode, let me know. Did I miss anything? Was there a topic I should have covered? Let me know at podcast@jumpstartnature.com or DM me on any of my social accounts. I'll do my best to answer your questions. You can find me at Nature's Archive, one word, on Instagram, Facebook, and Twitter. I also share photography, nature stories, and much more on those accounts, so you can follow just to stay in touch too. And despite being called crazy by numerous friends and colleagues, last year I left my tech career behind to start Jumpstart Nature, which Nature's Archive is now part of. For the sake of myself, my family, and the planet, I need to make this work. So please also consider becoming a patron at patreon.com/jumpstartnature. I offer some exclusive content and perks, and you can start donations as low as $4 a month. Lastly, please also check out our latest creation. It's the Jumpstart Nature podcast. We just completed our pilot season, where each episode reveals an unseen, surprising, or misunderstood nature topic with the help of experts and our host, Griff Griffith. It's entertaining and inspiring, and even reached number 3 on the Apple Nature podcast charts. There's much more on our roadmap, but we need your support, so check out jumpstartnature.com for more details. Thank you.